This is question 5 of the fall 2024 midterm. Here we have a cryptography question. Evan-Bot has invented a new block cipher mode of operation that they call AES repeated feedback mode. The formulas are given, and there's a quick diagram sort of explaining how this new cipher mode works. So first, for questions like these, what I think is very useful is to first just write out the decryption formulas for the scheme if they're not given. So here, what we can do is XOR both sides with a value that will hopefully clean up one side and just give us the answer. So the first line, we can do that by XORing each side with the encryption of the IV. And what this should hopefully do is cancel out some terms, so we're left off with just the encryption or decryption formula for that line. And we can do the same with the second line. This one we're just going to be doing it with this super big encryption term right here. Cool. And yeah, so we can sort of further understand what's going on here. Basically, the input is an IV into the first encryption block, and the output of that is being XORed with the first plain text block, and that output of the XOR is the first cipher block. And that cipher block is fed back into the sort of encryption scheme, hence the name repeated feedback mode. And then that's XORed with the original IV, and that goes into the encryption block again, and sort of we have this repeat process. Very cool. So the first question is, select the correct decryption formula for the ith plain text block. So we already solved this. It's right up here. Very nice. So we can sort of just choose the right answer, which would be answer choice A, or the first answer choice. For the second part, Alice has a 4-block message. She encrypts this message with our encryption scheme and gets back this ciphertext. During transit, there's a network error and it flips a single bit in C1. So Bob receives a sort of malformed ciphertext. So the question is, when Bob computes the decryption for the ciphertext, what will they decrypt? And so for this one, we can kind of go back to our formulas that we've written earlier. We'll copy paste them down for us. So we just want to look for the terms of P that are being affected by this sort of bit flip. We can sort of immediately see that what these formulas will become when we consider that there's a bit flip occurring is something like so. Yep. And so really what's happening here is that the new P1 is just going to be the original value of P1 with the XORed with 1. And we could also see that all of the other blocks of P are going to be garbage because this XOR of 1 is inside the encryption block. And so because even though one bit is being flipped, the encryption output is going to be something very different from the original value. And so what we're going to see is that we only have P1 that's sort of recoverable, and everything else is going to be garbage. Cool. Now we can move on to the third part. Alice has a 3-block message, and she encrypts it with our encryption scheme, receiving the ciphertext of the 3-block plain text. As Mallory, we want to modify the ciphertext C such that when it's being decrypted, the output is something of this form, XY1, where the 2 blocks that are decrypted are just any sort of value, including garbage, and the last block that's decrypted is always just 1. And we can see that Mallory, us, we have access to the original message P1, P2, and P3. And the question is select values for the modified ciphertext C prime, such that Bob will decrypt C prime into our target P prime value, which is just X, Y, and 1. So we can go back to our formulas. I'm going to paste them back down here. The goal here is that we want P1 to equal to some garbage, P2 equal to another piece of garbage, and then P3 equals to 1. And so because P1 and P2 can be garbage, we can sort of just ignore those 2 formulas and just focus on P3. We can write out the full original value of P3. And because we are using P primes, we should use C primes as well. We should write out the values of I. Like so. And as we can see, there's a lot of terms that are happening, and there's a lot of terms that we have control over. The easiest way is to sort of keep C1 and C2 constant because they're inside the encryption block. If we were to change these, then the output of this encryption block is going to be something very hard to know in advance. And so by keeping these constant, we sort of have a good idea of what this is. In fact, we have a great idea of what this is, because if we look back at our encryption schemes, we can see that the exact block is right here, as long as we keep the values the same as the original inputs. In other words, I'm going to let C prime of 1 and C prime of 2 to be the same values. And what this means is that this big chunk is going to equal to, and we can kind of see that over here, it's just going to equal to this part, right? If we XOR both sides with the C1 term, it's going to move over here, and we isolate the encryption term. So what we get is this, and these are not prime values because the encryption block themselves have non-prime values. And so putting this back inside the equation, we have something like this. And because we want to solve for C prime, we can just sort of isolate everything by XORing both sides with this. And so what we get is something like that. And so that's my final answer. Of course, keeping IV the same. And so that's what we can select. P3, C3, and 1. Moving on to the final part of this question, which asks us, what values of P prime can Mallory cause Bob to decrypt to, given that she can modify C and knows the original value of P? So very similar to the previous question, except now they're asking us all types of P prime, all forms of P prime that we can sort of use and exploit to achieve. And so the biggest important part of this question is to sort of look at how we did the original question. And so the basic idea is that we are modifying a single part of the original ciphertext in order to manipulate the output. And so what we can really see is that we can sort of use the same idea to modify the output value of P2. In fact, we can make P2 equal to 1 if we just make a small change in this sort of approach. And so we can sort of just immediately choose this value here as answer choice. But one thing to note is that in the formula over here, the inputs C'1 and C'2 are part of this formula, which means that if we wanted to sort of modify, if we wanted to not modify, for example, P4 of prime, that would be very difficult because C'3 would be an input to that formula, and because we're modifying C'3, the output, that value is not going to be the same. In other words, if we were trying to modify the second block of a 3-block message, the third block output, the plain text, is also going to be garbage. And so immediately we know that this is not, the second choice is not a valid answer because of that P2 right there. Also, on the very bottom right, that 1 is equivalent to saying we want it to be some sort of value. And again, for the same reason why we can't have that be P2, we also can't have that be 1. And that same sort of logic goes for that answer choice. And so the remaining answer choices do not have that sort of restriction where we want to place a certain value after the 1. So these are all valid. And the main reason behind the logic is because of this big formula right here. Cool. And that is question 5 of the fall 2024 midterm. Thanks.